Long-term goals are harder to focus on. Making developers' work easier is rarely a priority. And after all, tracing is not shiny. It's quite obvious. Tracing can help us detect problems and why they happen, but these are long-term goals. Sooner or later, most public-facing systems will crash, probably at a client in a different continent. You are now faced with a few megabytes of log files from different machines. You read the bug description, and it says, not working. You spend hours until you find an exception, and it's still hard to be sure. This means we are all in danger of being interrupted while drinking our gin tonics because tracing is buried in the backlog. I understand that in Warsaw it's in the middle of vodka, but it was written for the Dutch crowd. No, I'm kidding. So, after all, laziness is good in the software world, right? Still, all software organizations are trying to get logging right, and this effort gave us different solutions for this problem. First, let's look at traditional loggers. Anything from print line to log back. It's simple to set up, and after you master the configuration format, you still have to manually put logging statements all over the place. These statements then create files that you must parse, often by hand, and the file problem is compounded in a distributed system. We have a front end, 2 middle tiers, and 2 backends. Each letter is a cluster of machines. So when a user initiates a request to front end, 2 calls are sent to server B and C. B can respond right away, but C requires a response from backends, D and E, before it can reply to A. A simple yet useful distributed trace for this request would be a collection of message identifiers and timestamped events for every message sent and received at each server. This was taken from the Google Dapper paper. I'm going to talk about it soon, and you should read it. So Gregor Kizales and colleagues from Xerox created AspectJ in order to relieve themselves from the tedious process of writing log statements, an aspect-oriented programming implementation. As the name suggests, it allows running arbitrary code in aspects of your program. AspectJ exposes 3 API methods for executing code before, after, or around any function in your application. It's confusing as it sounds. This means features can share code. The shared code can be traced in one place with one function. The Java agent will inject the code at runtime. And Kamoon is a great project. It makes use of this technique. It lets you wire JVM application and even has Akka and Play models. But it's doing something I wanted to avoid. You have to add a Java agent to your deployment. It changes the application, the way the application is deployed, and it complicates things. It's not the Bible. 9 years later, 9 years after the guys from Xerox came up with aspect-oriented programming, Benjamin H. Siegerman, an associate from Google, noticed users really hate waiting. So we have to detect latency problems quickly and efficiently. And that most engineers can't be experts in many systems, so a unified interface for infrastructure diagnostics can help us diagnose these problems quickly. The proposed solution, dapper, has 4 parts: UI server, tracers, spans, and annotations. A tracer is an entity that collects spans and sends them to a UI server. Each span can hold an arbitrary number of annotations with information about a trace. These annotations are a map of keys and values, and they can hold what you would normally log, like incoming payloads, query strings, or errors. Although collecting these spans and annotation is not computationally intensive, logging every request will put some stress on network and CPU, which will lead to degraded performance. A simple solution for dealing with this problem is sampling. For Google scale, every 1,024 requests was enough to capture the vast majority of interesting events. I have a friend from back home in Tel Aviv. He's a graffiti artist. Yeah, I lied. I'm originally from Israel. I have a friend back home in Tel Aviv. He's a graffiti artist, and he visited me in Amsterdam. He was hoping to bomb some walls, but found it difficult to be the first one to tag a wall in a neighborhood. So I said it's the same with tracing. You don't want to be the only one with opaque features, which will make tracing everything the norm. So another important take from Dapper paper is to have pre-instrumented building blocks developers can reuse. Using these blocks, developers don't have to think about instrumenting the application. It's already there with a standard tracing system in place. It's easier to add the specific information you need to trace your feature. Zipkin is an open source software implementing the open tracing standard, which is based on dapper. Zipkin helps gather timing data needed to troubleshoot latency problems in microservice architectures. It exposes an API which receives spans and annotations from tracers and a UI to explore these collected spans. You don't have to use htrace to send data to Zipkin, of course. There's a library in almost every language and big and helpful community which will help you connect using your favorite tracer. So we have an idea, a standard, and an ID which is dapper, a standard which is open tracing, and a server that implements the standard which is Zipkin. Now, all we have to do is send spans to this server so we can analyze our traffic. Luckily, the good people at htrace have our back. htrace is an Apache incubator project which implements interfaces to send traces to backends, including Zipkin. More importantly, htrace implements convenience wrappers for multiprocessor programming, like a wrapper for execution services and a wrapper for callables. Having these low-level building blocks meant I only had to write a little bit of code to glue the Actor system dispatchers to the trace executor service in order to instrument Akka stream applications. So why do we need another library for tracing? I wanted to avoid manual work, because I'm lazy, and didn't want to change anything about the way I deploy my applications. My goal was to have flows and Akka HTTP endpoints traced with only a simple configuration change. The trace executor service was a great starting point to trace threads. All I had to do is implement an executor service configurator class that creates an execution service using the tracing executor. So let's see a demo. Okay. We start with the stream example. Can you see what's going on there? Come on. Big. Well, there's nothing special here. There's an Actor materializer.
Can't see it.
Oh.
Too small.
Okay. Thank you for telling me. How the hell? Sorry? Oh? Yeah? Just help me, my man. Oh, nice. Thank you. So, you can see it's my first time presenting. Okay. We have a source. We square 1 until 10 iterator. And then we run a fold async. So we will get back our iterator squared. Nothing fancy. As you can see, I lied a little bit. You have to initiate the scope. Okay? So we expect to see several threads working on squaring these, right? So let's see if we can make this work. Okay, we have all sorts of tracing data, and this is the list of integers. There's 16, 9, that was squares. And this is Zipkin. It was, like I said, it was initially implemented by Twitter, and now it's part of the Open Tracing project. So we have 9 spans, which is nice. We can click on it. We have the whole compute span that we've seen before. Compute. And we can see things running almost in parallel. So one nice thing I learned when doing this demo was that I had to add the async keywords in order to actually run this in parallel, or actually run it in 9 threads or 8 threads. So I got it crazy. I tried to remove it, and this should show a bit of how you can use zipkin and in unexpected ways. So let's see. Again, traces. As you can see, there's only 3 traces now, and it's not running in parallel. Unfortunately, I don't really know to explain why it's happening exactly like this. I know that the async is the border for async computations, but maybe some expert can tell us later. So. Yeah, I also noticed that. The materializer is, well, there used to be like a thread sleep here, but it's not doing what you expect. You would expect to have like 9 100 milliseconds, let's say, spans, and it's not what it's doing. It's because of the actual materializer. So the second thing, and to me a little bit more exciting, was the HTTP example. It's also quite simple. All I did was tell Akka which dispatcher I want to use, the tracing dispatcher, which is just a configuration value like any other Akka dispatcher. We have a front-end route, and we have a back-end route. This one is doing factorials. So what we want to see now is that I send a request to the front end. It will go to the back end, and we'll see the whole trace in one spot. And we'll see what takes the most time. So let's see if it works. This is just 8080 front end. We have this list of factorials, right? And now when we'll find traces, the newest one first. This is exactly what I want to see. We have a spanning the whole front-end time, all right? And then 4 milliseconds later, it was sent to the back end. And here, I do have this thread sleep. We can see exactly 100 milliseconds later, we have 9 threads working in parallel, computing factorials. Amazing. That's it. Well, I cheated a little bit. What I wanted to do is that you can send any kind of RPC, and you will have tracing out of the box. As you can see, you have to add a header. It's pretty easy, but you have to add a header to mark this RPC call in order to have this kind of visualization, that it's connected. Okay. So it worked. That's it. Thank you. Check out the incubator htrace. It's a really nice library you can instrument your applications with. Definitely check out Kamoon. It's really nice if you are willing to use Java agents. It gives you a lot out of the box. You can follow me on Twitter, and if you want to work in Amsterdam on cool things, you can send me an email or just talk to me after this. Thank you.